Dos.
A capacitor is a device that stores electric potential energy and electric charge. It is formed by insulating two conductors from each other. In a circuit diagram, we could find either this symbol or this one would be the node on the positive sign and the negative side. So how does the capacitor store this energy? Well, if we transfer a charge from one conductor to another, we would have this energy storage, leaving one conductor with a Q positive charge and a Q negative charge. It is important to say that this Q have the same magnitude, and the work done to move one charge from one plate to another, it's called electric potential energy. Well, the capacitance is how good this capacitor storages energy, and it is given by the charge over the potential difference, that would be Coulomb over voltage, the well-known Farad. And in vacuum, we can find that the capacitance is given by the air permittivity times the area of the plate over the distance that these two plates are separated by. We can see that in this diagram, in which we can find plate A and plate B separated by the distance d. We can see that the charges in this plate are positive and in this other one are negative, since we're creating a potential difference that it's called B sub AB. Well, this would be the wire that it's connecting the capacitor. And this diagram would be known as the parallel plate capacitor, that it's the basic capacitor that we get to know in circuits and in electricity and magnetism. We also have the spherical capacitor, in which we can calculate the potential difference by a Gauss super area, and it is given by the charge over 4 pi times epsilon sub 0 times 1 over the radius a, that would be the distance from the center to the positive plate, and then RB, that would be the distance from the center to the negative plate. And we also have the cylindrical capacitor, which is given by a lambda positive charge cylinder and a lambda negative charge cylinder. The potential difference is given by lambda over 2 times pi times epsilon 0 times natural logarithm times the distance from this one to this one, that would be RA, and RB, that would be the center to the negative cylinder. We can have that capacitors are arranged either in series or in parallel. Well, capacitors are given by the inverse sum of each of them, that would be the equivalent capacitor in a circuit, and in parallel we would just add them up, so we could obtain the equivalent. So here we have an exercise in which we are asked what is the total charge the power source must apply to the charge to charge this arrangement in the capacitor. A good tip that I use in order to find which elements in the circuit are in parallel and which ones are in series is to color the nodes that are tightening them up. For example, this one would be a node, and it's going to this one. So now that we have all colored, we can now easily see that these two capacitors are in parallel, since they are sharing the same two nodes, and these two ones, the 18 and the 11.3 are also in parallel, and if we add them up in parallel, we will find like an equivalent here and equivalent now here that would be in series. But let's do that so you can see it. First, in this problem, we need to find the equivalent capacitor. So we would just add what is in parallel and add what is in series. So if we sum 33 microfarads and 44 microfarads, we would obtain, I'm gonna erase this, we're gonna obtain an equivalent of 77 microfarads. I'm just gonna put it like this. And if we add these ones up, we sum them, we would obtain 19.3 microfarads. I'm just gonna erase this. And if I use my colors again, we can see that this one is a node. This also would be another node. And the red node, I'm just gonna mark it again so you guys can see it. Well, this is the wire that I omitted by erasing. So we can now see that these two capacitors are in series. So we would have to sum the equivalent of them. And we can do this by adding them up like this. That it would be 1 over 77 microfarads plus 1 over 19.3 microfarads. The equivalent would be equal to 3 microfarads. Now that we have the equivalent, we're gonna use this formula over there to calculate the amount of charge that is needed so that the arrangement of capacitors are charged. So solving for Q, we would obtain that the charge is equal to the capacitor times the capacitance times the potential difference. And since I've already gave you what that was, it's 0.2 microfarads, sorry for this, times the potential difference that they already told us which one is it. And that would be the answer. I'm gonna write it down here. That would be 2.12 times 10 to the minus 4 coulombs, and that would be the answer for this problem, in which we had a capacitors in series and in parallel, and we also had to use the formula for obtaining the charge in the capacitor and the potential difference. So now moving on into something else, we can see that some formulas that are also important to this topic are potential energy stored in a capacitor, that is the work done, and we can like make a resemblance of how a spring is compressed, and this would be the work, well, the potential energy done in the spring, but this would be the potential energy done in the capacitor so that it charges the potential energy. We also have that the electric energy density in vacuum that will be given by this, and it is also important to say that we don't always have vacuum as an experiment, so this would be a constant in laboratory works and etc. We've been talking about capacitors with just vacuum between the two conductors. But what happens when we put a dielectric between them? What is a dielectric? A dielectric is a non-conducting material that it's put in between the two conductive plates, and this helps us to maintain the two conductors separated. And we also need to know that there is just a tiniest distance between these two conductors, so that's like a lot of work. It also increases the maximum potential difference between the two conductors, and the capacitance is greater. Well, the dielectric constant is a term that is given already in many tables, but we can obtain it by dividing the capacitance with the dielectric over the original capacitance. But how do we obtain this capacitance with dielectric? Easy. We can obtain it by this formula, that it's the permittivity of the dielectric times the area over the distance of the plate. And we also need to know that the electric energy density in the case of the dielectric is given by the permittivity of the dielectric times the electric field over 2, that is given by this formula. And I'm going to erase this so that you guys can see a diagram of how polarization is given. So imagine we again have our positive plate and our negative plate. Oh, this one's black. I didn't want it black. I want it blue. And the negative plate. I'm gonna put some negative signs. And here's some positive signs. So this would be the original capacitance, in which we know that these two are constantly attracting, and this makes the potential difference between the two conductive plates. So many arrows are happening right now. And this would be vacuum. So when we add a dielectric between the plates, I'm gonna do the diagram again. This would be one plate, and this would be the other plate. We already know which one's positive and negative. This would be our dielectric. But we also need to know that the dielectrics are not neutral. They also have charges. So the redistribution of these charges would go like this way or this way. So we would have positive, 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 negative, negative. But we'd also have some negatives over here and some positives over here. But this doesn't mean that the capacitance is gonna change its charge and it's always gonna remain neutral. The only thing that this means is that there is a redistribution of the charges happening in this capacitor, and that is called polarization. Thank you.